this lesson, we discuss various techniques to compute efficient frontiers. We start the discussion by providing the motivation for discussing three important scenarios, including various combinations of short sale restrictions and risk-free lending and borrowing cases. We start with the most simple and ideal case, that is short selling in the fullest sense and risk-free lending and borrowing at infinite amounts at the same rate. First, we'll discuss a simple visual proof to provide the intuition for the optimum portfolio in the presence of risk-free lending and borrowing. Then we discuss a more mathematically rigorous proof to find the solution to the optimum portfolio problem in the presence of risk-free rate. We'll also discuss this optimization procedure with the help of a simple numerical problem. In a similar manner, we'll also formulate the conditions for the following short sale allowed but no riskless lending and borrowing. We'll also briefly discuss the two cases of short sales not allowed in the presence and absence of riskless lending and borrowing. Both of these problems require quadratic programming and the mathematical proof is out of scope of discussion. We'll only offer the intuition to the optimization problem and formulate the objective function and constraints. We'll also apply our understanding of slope maximization problem in the presence of risk-free rate to provide a rigorous proof of standard CAPM. Then we close the discussion with concluding remarks. In this video, we'll provide the background and motivation for computing efficient frontier. Let us recall and summarize our understanding of mean variance framework obtained in previous weeks and lessons. So we have, for a given set of securities, we have their expected return on y-axis here and risk on the x-axis. Now if we plot all the possible combinations of these securities, we get portfolio feasibility region like this and a minimum variance frontier like this. Why we are calling it as a minimum variance frontier? Because every point on this minimum variance frontier represent a point where for a given level of return it gives you the minimum level of risk, and that is why it is called minimum variance frontier. On this minimum variance frontier, starting from this global minimum variance portfolio which has the lowest risk across all the portfolios on or securities on this minimum variance frontier, and also another point which has the highest return across all the securities, this region, this particular portion of the curve is called efficient frontier because each point on this efficient frontier gives us the best risk return combination. For example, for a given level of return it offers the lowest risk, and for a given level of risk it offers the highest return. So this is our efficient frontier. This discussion is part of mean variance framework. However, while it's visually easy to examine, how to trace mathematically this efficient frontier, that is of paramount importance in this mean variance framework. To a complete understanding, comprehensive understanding of mean variance framework, it is of paramount importance that we understand how to estimate this efficient frontier, how to mathematically understand and estimate this efficient frontier. We'll try to explore some simple techniques that will help us trace this efficient frontier in a more simple manner with some computer programs and some mathematical modeling. As a part of this routine, we'll not discuss all the cases. We'll keep ourselves fixated on some of the important cases. So we start with an extreme case where short sales are allowed and riskless lending and borrowing is also allowed, which is an extremely theoretical kind of case, not a very true depiction of real markets. Then we'll move one step where short sales are allowed but riskless lending and borrowing is not allowed. The third case where short sales are disallowed but riskless lending and borrowing is allowed. And lastly, we move to another extreme case where neither short selling nor riskless lending borrowing is allowed. So to summarize this video, we discussed the mean variance framework and the importance of efficient frontier. And we noted, due to its importance, it is necessary and of paramount importance to understand how and what techniques are employed to estimate and trace this efficient frontier. In this video, we'll introduce the problem of computation of efficient frontier in the presence of short sales as well as riskless lending and borrowing. Recall the analysis of efficient frontier and portfolio feasibility region, that in the presence of risk-free asset, there was one portfolio, B, market portfolio, which was the dominating or the best portfolio across all the securities. And in the presence of this risk-free rate, a new set of efficient frontier which was dominating the previous efficient frontier was traced. So this straight line was the new efficient frontier. Visually, this efficient frontier is nothing but a tangent line from RF to B. and it extended the possibilities beyond. So any combination on this line is a partial investment in RF, that is lending segment. So partial investment in RF and partial in B will lead to a position on this lending segment. If we borrow at RF and further invest in B, not only the original wealth but borrowed amount, then we can extend our position on this part. So essentially the portfolios on this line RF to B is the new efficient frontier, which carries the portfolios that are dominating or best across all the portfolio of risky assets. So the original efficient frontier is dominated by this tangent line, and this is the new efficient frontier, which is RFB and extended beyond. Okay. The key property of this line is that slope of this line is the highest. And what is the slope? The slope of this line, any point on this, let's say this portfolio B, so the slope of this line is RB bar minus RF upon sigma B, which is the risk of this portfolio. So in essence, when we are trying to find the slope of this line, what we are doing is we are maximizing the slope quantity, which is the excess return over risk-free rate divided by risk. So for any generic, let's pick any generic point P, the slope is RP bar, which is the expected return on RP minus RF. So this is the excess return over RF and the risk of portfolio sigma P. So what we are doing, we are trying to maximize this quantity, and the point at which this is maximized will be the tangent point, and at that point the slope will be maximum and will give us the most optimum portfolio. To summarize this video, we discussed the most interesting and most simple case of efficient frontier, where the short selling is allowed as well as risk-free lending and borrowing is allowed, and therefore one and only one portfolio, which is the tangent portfolio at which the slope of line connecting the risk-free rate and this tangent point is maximum, is the solution to the portfolio problem. Once we find that point, we maximize the slope and we find that point, then we can easily trace the new efficient frontier, which is the straight line going from RF to the tangent point B here and beyond. In the previous video, we discussed the visual intuition behind the approach to obtain efficient frontier or trace the efficient frontier in the presence of short sales along with the riskless lending and borrowing. In this video, we'll provide the mathematical formulation and discuss the mathematical approach to find the efficient frontier. Recall our previous discussion. In the presence of short sales as well as riskless lending and borrowing, we said our problem or objective simplifies to maximizing the slope of the portfolio that connects risk-free rate and any point on efficient frontier. So if there is a generic portfolio P, the slope of line connecting risk-free rate and that portfolio point P is RP bar, which is RP bar is the expected return on point P minus RF. This is the excess return over risk-free rate divided by sigma P, which is the risk. Now ultimately our problem simplifies to maximizing the slope with a constraint that our overall wealth is 100%, that is individual investment into securities I equal to 1, 2 and so on up till n should sum up to 1, that is summation xi equal to 1, which is the wealth constraint. So overall amount of wealth is 100%. This is something similar to constraint maximization problem, and one can use computer programs with Lagrangian multipliers to solve this. However, there is an easier way to solve this problem by substituting this constraint into objective function and making this as unconstrained problem of maximization. Let's see how it is done. So we'll start with the objective function. In this objective function, please note RP bar, which is the expected return on portfolio, can be broken into its constituent expected returns, that is xi into Ri bar summation. This we have already seen, where xi's are the respective weights invested in security I and Ri bar is the expected return on security I. Now a simple trick that RF is the risk-free rate. It is not stochastic, so you don't see any bar here, it is fixed. But we can break it down in a very simple manner to xi into RF, where xi's are the proportionate amount invested in security I. How it is done? Let's say RF was fixed at 10% and there were 3 securities I equal to 1, 2, 3, where 50% was invested in 1, 30% in 2 and 20% in 3. Given that summation xi equal to 1, I can simply write this notation where each of the xi is multiplied, fraction multiplied by 10%, which will give me essentially 10%. This is why, because summation xi equal to 1. And therefore, I can replace this expression here at RF to get this kind of expression. which is xi into ri bar minus rf upon sigma p. And so now I have created an unconstrained maximization problem by incorporating the constraint in my objective function here. And I got this expression where sigma p is square root of xi square sigma I square summation plus xi xj sigma ij, where I is not equal to j. This we have already seen in the previous portfolio discussions, that this is the expression of risk of portfolio with n securities. Now all we need to do is maximize this expression with respect to all xi's. So ultimately our problem leads to the following system of equations where the theta function, which is the slope function, is maximized with respect individually with respect to all xi's and put equal to 0 to obtain the sort of maxima. And this mathematical formulation has a solution with some properties of differential. As we'll see in the next video, we'll see the approach how to arrive from this original problem to the solution, this solution we'll see in the next video. But ultimately it will lead to this simple expression where d theta as a differential of xi, which is the proportionate amount invested in security I, is nothing but minus lambda x1 sigma I1, where this is the covariance of security 1 with I, covariance of security 2 with I, weights invested in 2, and lambda is a constant, plus ri bar minus rf equal to 0. So we obtain this simple solution, but how to reach from this point to this point we'll discuss in the next video. But ultimately this is a very simplified solution. For example, for security I equal to 1, this expression will lead to this d theta upon dx1 equal to minus time this expression plus ri bar minus rf equal to 0. Now the mathematical solution, a generic solution, this solution will have n such equations, and we'll use a simple trick by using or putting lambda times xi. Notice this lambda x1, lambda x2. We'll replace this generic lambda xk terms with zk, where zk is proportional to xk, and therefore the resulting equation is, generic equation is ri bar minus rf equal to z1 times sigma 1 I and plus z2 times sigma 2 I, and so on up till zn times x and I. The n equations corresponding to this generic formulation can be written like this. For example, for security I equal to 1, the expression will be r1 bar minus rf equal to z1 sigma 1 square, z2 sigma 1 2, and so on. Notice there is the only variance term comes for I equal to 1, so z1 sigma square. So let's say for I equal to n, the expression is rn bar minus rf, and the variance term will come only with zn, so zn into sigma n square. So you can think of any generic security I, and the variance term will come with only ri bar minus rf equal to summation of terms and only zi sigma I square. So only variance term, one variance term will come in equation I. Now these are n equations, system of n equations and unknowns that are zi's. So we can solve this equation to obtain the value of z. Let's say you get the value of zk and all the zi's. So we can extract xk's from these values of zi's. How? So each xk will be equal to zk upon summation zi. This is so because zk is lambda times xk and the denominator will be lambda times 1. So ultimately we'll end up with xk only. So from this n system of equations we can first obtain all the zi's, and using those zi's we can further obtain xk's, which are essentially the optimum proportions invested in each security. I repeat, that was our ultimate objective, to find those optimum weights that leads us to that tangent portfolio where weights invested are x1, x2 and so on up till xn. So these xk weights or xi weights are the optimum proportions invested in each of the security in the tangent portfolio, are obtained from solving this system of equation. To summarize, in this video we mathematically formulated our problem of tracing the efficient frontier, and we saw how to maximize the objective function, that was the slope, and through a simple trick we could obtain the optimum proportions invested in each of the securities, that is xi's, which ultimately lead to identification of this optimum tangent portfolio. In the previous video we discussed our constrained maximization problem. We formulated our theta function which we planned to maximize, which was rp minus rf upon sigma p, rp bar minus rf upon sigma p. We also saw the mathematical solution for this problem, a very simple mathematical solution. In this video, we'll discuss and derive this solution mathematically in a more rigorous manner. Let us recall the optimization problem that we discussed. So basically we tried to solve for the slope function theta. This theta was the slope function where the value of theta was summation I equal to 1 to n, xi rp bar minus rf upon sigma p, where we were trying to find the maximum value of theta with respect to the variable xk, or the proportionate amounts invested. Here, sigma p is the risk of the portfolio, which can be given by this expression summation xi square sigma I square and summation I and j xi xj sigma ij. So these are two components to this risk function. In the second component, notice that I is not equal to j and raised to the power half. So this is the customary risk function that we have already seen. But interestingly, please note, this is a combination of two expressions. So there's something in numerator and something in denominator. So this function fx is a combination of two functions f1x and f2x, where d by dx is, with a simple chain rule, we can write f1x equal to d of f2x upon dx, which is the derivative of second function multiplied by the first function, and f2x into d of f1x upon dx, that is second function multiplied by derivative of first function. This is simple chain rule of differentiation, so we'll make use of that. Now here, recall f1x, we have considered the numerator, which is summation I equal to 1 to n xi into ri bar minus rf. This is our numerator. And denominator f2x is the risk function, which is summation xi square sigma square I1 to n, and I1 to n summation and j1 to n summation, where I is not equal to j xi xj into sigma ij raised to the power minus 1 by 2. The derivation of first part is rather simple, that is f1x d of f1x upon dxk. In the entire complex looking summation expression, there is only one term which carries xk, with respect to which we are differentiating. All the other terms are basically constant for this differential and they will become 0. So only one term where this xi is xk will remain, and will get, corresponding to that expression, will get rk bar minus rf. So it will be something like xk into rk minus rf. Only this expression will survive. For all the xi's that are not equal to k, they'll become 0. So only this expression will remain, all of them will perish, and we'll end up with this one. But the differential of df2x by dx is slightly more involved. Let's see that. Let's start with a simple 3 security kind of expression for sigma p square. So if this is the expression, ultimately we are trying to differentiate the risk expression sigma p. So this is the expression for 3 securities. If we would have differentiated with respect to x1, we would have got 2 times x1 sigma 1 square and x2 and x3. So essentially, recall, this expression will become 0 if we are differentiating with respect to 1, and what we are and will end up with is nothing but x2 plus x3. That is, you will end up with, so basically this term will perish and you are left with this one and this one, which is nothing but 2 times 2 into x2 plus x3, and x2 will be multiplied by sigma 1 2 and x3 will be multiplied by sigma 1 3. It is sort of 2 times summation I 1 to n, where I is not equal to k, and inside you will have summation x I sigma I k, something like this. So this is what we get here. So when we differentiate here, the first term, first and foremost, so for example, this term will sustain 2 times x1 sigma 1 square, so we'll end up with 2 times xk sigma k square, the generic term, and in the remaining, these terms will become 0. In the cross terms, we'll only end up with these 2 terms, or with n terms, we'll end up with n minus term. Why n minus? Because one term where j is equal to k will not be there. So this is only true for j not equal to k, and we end up with the expression. So this is also solved now. So ultimately, our two expressions, that is, we started with f1x equal to this and f2x equal to this. We noted that d of f1x upon dxk, the generic expression is this, and for df of f2x upon dxk, this is this. Now, apart from this expression, recall that there is also a power of minus half. So this power of minus half will come out here and it will be subtracted by 1, so it will become minus 3 by 2. So this is our overall expression for the sigma p function that we differentiate with respect to xk, that was in denominator. So let us put them together. This was our combined expression. Let's put it together. Let's put in the values. So this is the first part up till here, which we saw, and this is the second part. Now in this expression, if we multiply it by this part, this will get neutralized, and here we'll get the power of -1. And what we can do is we can further take this negative side on the other side RHS. We have put this expression equal to 0, so we can take this on the other side. So we end up with RK bar minus RF, which is this term. This we have already multiplied with the complete expression, so this is neutralized, and here we get the power of -1, which is something like this into this. So we end up with this expression. Now here we can define lambda as this expression. This is our lambda. We defined this lambda because it's rather constant. Notice that this is nothing but your Rp minus Rf, and in denominator you have sigma p square. So it's sort of constant, and we replace it with lambda. So we get a very simple looking expression like this. Now further what we'll do is we'll open it for lambda, and we get this broad generic expression that we have already seen in the previous video, where we multiply lambda. So it's the generic expression is lambda x1 sigma I1 plus lambda x2 sigma 2 and so on up till lambda xn sigma ni, where the ith term becomes lambda sigma I square xi. Let's further simplify it. So our broad generic expression, the partial differential with respect to each of the xi. Earlier we were looking at only xk, but all xk would take values 1, 2, 3 and up till n, and all of them will be put together equal to 0. So we have a broad set of system of equation and equations corresponding to each of the k, and it will appear like Ri bar minus Rf equal to lambda times x1 sigma 1i and so on up till lambda times xn sigma ni. All the terms are covariance terms, only one term is the variance term. That is important to note. And we'll have n such equations where lambda is a constant, and we can substitute, further simplify lambda xk equal to zk. Recall that xk here are the fractional amounts invested in the securities, and when we replace lambda xk equal to zk, the resulting expression appears to be like this. It's easy to understand. Ri minus Rf equal to z1 sigma 1i r2 z2 sigma 2 and so on. Now this generic Ri minus Rf equation, which is appearing like this, we can also have n versions like R1 bar minus Rf, R2 bar minus Rf and Rn bar minus Rf and up till n equations, and these equations will appear like this in a very simple manner. Now note here, when we solve this n system of n equations and n unknowns that are z1 z2 up till zn, we'll get the values of zi's. Now ultimately the aim is to solve for xk. Now that we have the values of zi's and zk's, we can solve each zk corresponding to its value of xk like this, because summation zi is equal to 1. So it is something like zk is equal to lambda times xk, and in the denominator we have summation lambda times xi. So lambda will come out and the summation xi equal to 1, so it will be only xk itself. Lambda will cancel each other, so it will be only xk. So it's very easy to solve. So just to conclude this video, we saw sort of numerically rigorous derivation of this solution to the slope maximization problem. We tried to maximize this slope which was Rp bar minus Rf upon sigma p. Through some tricks, mathematical tricks and simplification, we could solve it in the form of n equation and linear equations and unknowns, and we can easily solve for xk. Once you have the xk, you can find Rp bar, as we'll see in next set of numerical examples in subsequent videos. We can solve for sigma p, and once we have Rp and sigma p, we can further obtain the theta value, which is the most optimum solution or the market portfolio. In this video, we'll concretize our understanding of computation of efficient frontier with short sales allowed with riskless lending and borrowing case with a simple example. Let us look at the details provided. So we are considering three securities A, B, C. We can also call them 1, 2 and 3 along with the risk-free rate. We have been given the expected returns on all these instruments along with the risk-free rate and standard deviation or risk of these securities and correlation across AB, AC and BC here. All we need to do is formulate the three equations for finding the optimum proportions. Recall that these were the equations: R1 bar minus Rf equal to Z1 sigma 1 square, Z2 sigma 1 2 plus Z3 sigma 1 3 and so on. In this case, there are only three securities, so we'll have system of three equations and three unknowns, that is Zi, Z1, Z2, Z3. So let's substitute the values. So for example, the first equation is R1 bar minus RF equal to Z1 sigma 1 square, Z2 sigma 2 and Z3 sigma 1 3. So we know RA is given to us 14% and RF is 5%. So R1 bar minus RF is 14 minus 5. Then we have Z1 into sigma 1 square. So sigma 1 square is 6 into 6. Then Z2 into sigma 1 2. Now this is covariance. So covariance is Z, sigma 1 2 is rho 1 2 correlation into sigma 1 into sigma 2. So rho 1 2 or rho AB is given as 50%. So we'll use 0.5 and sigma 1 is 6 and sigma 2 is 3 or sigma AB is 3. Similarly, Z3 we have sigma 1 3. So we'll use rho 1 3 into sigma 1 into sigma 3. So here rho AC is given as 20%, so we'll use 0.2. I'm just substituting A, you can think of 1, B as 2 and C as 3. So sigma 1 or sigma A here is given as 6%, so we'll use 6 and C as 15, so I can use that. Just recall, while doing the mathematical computations, either you stick with the absolute values like 6, 15 and so on, or you use 0.06, 0.15, whatever value you choose, you stick to that and ultimately you'll end up with the right result, whatever approach you may have. Similarly, similar to the expression 1, we can also substitute in expression 2 and expression 3 and get these three equations. Now all we need to do is, with these three equations and three unknowns that are Z1, Z2, Z3, we can solve them very easily. Any simple calculator, mathematical calculator or Excel will do the job. You'll get the values of Z1, Z2, Z3. So Z1 is 14 upon 63, Z2 is 1 upon 63 and Z3 is 3 upon 63. Now let's see how using these ZIs we can solve for Xi. Recall in our previous discussions we said that any lambda xk is zk and therefore we can solve for these xk's by writing this expression zk upon summation of zi. So similarly we can solve for x1 as z1 upon summation zi and x2 as z2 upon summation zi, and we can get these values of x1 as 14 upon 18, x2 as 1 upon 18 and x3 as 3 upon 18. So now what we have is xi's, or rather x1, x2, x3, which are the proportionate amounts invested in that optimum portfolio, that tangent portfolio. We have the weights x1, x2, x3, proportionate weight invested in these portfolios. Now it's very easy to identify the expected return on portfolio, which is x1 r1 bar plus x2 r2 bar plus x3 r3 bar. Similarly, the risk of the portfolio can be obtained with x1 sigma 1 square, x2 sigma 2 square and so on, and then the covariance term. 2 times rho 1 2 x1 sigma 1 x2 sigma 2. So we can now compute this, and the slope is rp bar minus rf upon sigma p. Since we have now rp bar and sigma p, we can get the slope value as well. Let's see how these numbers look like. So first we compute the rp bar, which is the sum product of weights and expected returns, which is 14 upon 18 into 14 and so on up till 3 upon 18 into 20. So here we get expected return as 44 by 3%, which is close to something like 14 point something in percentages. Then similarly I can obtain sigma p square by substituting values in this expression, where we know x1 is 14 upon 18, sigma is 6. So I can substitute the values from the table and get the value of sigma p square as 203 by 6. So here the square root of this will be the sigma p in percentage terms. So I can obtain the slope as rp bar minus rf upon sigma p by putting these numbers. Notice, because numerator and denominator both are in percentages, I do not have to explicitly put them in fractions. Both of them are percentages, so I'll get the ratio number as 1.66. So this 1.66 is the slope of the tangent line that we were trying to identify, and we have also identified the proportionate amounts invested, that is x's, and we have identified the rp bar, the y coordinate of this portfolio here, as well as the sigma p x coordinate. So we have completely identified this optimum portfolio. To summarize, in this video, with a very comprehensive numerical example, we saw with the given data of expected return, risk and correlations, how to work out when risk-free rate is given, how risk-free lending and borrowing is given, how to work out the optimum portfolio, how to identify the optimum portfolio. And once we identify the optimum portfolio, all we need to do is find the slope of this line. The slope is the new optimum efficient frontier. So essentially, when we have identified this optimum portfolio with its weights along with the risk-free rate, the line connecting this, as long as we know the slope, we have identified this efficient frontier, which dominates the set of risky security. In the next two videos, we'll try to compute the efficient frontier in the presence of short sales, but no riskless lending and borrowing. In this video, we'll see a more visual and simple and intuitive proof, and in the next video, we'll look at more rigorous, mathematically rigorous version of the proof. Let us recall the original mean variance framework and minimum variance and efficient frontier. On the expected return and sigma risk graph, we noted that we obtain an efficient frontier where each point corresponds to a unique risk return combination, where at a given point we get the minimum risk for a given level of return or maximum return for a given level of risk. That was the property of this efficient frontier. And for a given risk-free rate, let's say a risk-free rate was given in the previous case, and then we could identify one particular portfolio that was best among all given that risk-free rate. Now we can replicate that analysis, but in that case, for hypothesized risk-free rate, we can hypothesize the risk-free rate, and for each hypothesized risk-free rate, we can obtain a tangent portfolio on the efficient frontier. But by the back calculative logic, this tangent point will ultimately be a point on that efficient frontier itself. For example, if 6% were to be the rate, the tangent point, the tangency point that will go through this C would be essentially an point on efficient frontier. However, in case there was a risk free rate 6%, then this would be a market or sort of dominating all portfolio. But we are assuming that this is a hypothetical rate, so this is rather point on efficient frontier only, not best among all, but just a point on efficient frontier. Similarly, we can trace another point at 5% risk free rate, hypothetical risk free rate. We can trace a point B, which is tangent, and so on for 4%, and thus we can trace the entire frontier. So we can keep on changing the risk-free rate, hypothesize risk-free rate, and trace the entire efficient frontier. But a simple mathematical logic, simple logic of our financial property will help us. While we can compute the efficient frontier by taking all the risk-free rate and obtaining the tangency portfolios, but please remember that the property of this efficient frontier, any combination of two efficient portfolios, 1, 2 is efficient. Or in generic manner, if we pick any two efficient portfolios on the efficient frontier, their combinations are efficient itself, and therefore all we need to trace the entire efficient frontier is two portfolios, maybe A and B or B and C, and then further combinations of these portfolios will help us trace the efficient frontier, with one caveat that the short sale restriction here is in a very generic sense, that is, fullest short selling is allowed in the fullest sense. Any amount of securities can be sold short as much as needed. Now, once you believe in this, then all you need to do is find two risk-free rates, two RFs. With the help of these two RFs, trace two tangency points on this portfolio. And then once you have those two efficient portfolio, you can mix them in different combinations to identify the entire efficient frontier. In this video, we discuss a simple financial property or financial logic that if we could identify two efficient portfolios on the efficient frontier, then we can trace the entire efficient frontier. So all we needed to identify these two efficient portfolio is two risk-free rate, RF1 and RF2, and once we have these two rates, we could identify two portfolios, and then further we could get the entire efficient frontier. In the next video, we'll discuss a mathematical proof to this logic. In this video, we'll carry on our analysis of efficient frontier in the presence of short sales but no riskless lending borrowing in a more empirically rigorous manner. Recall in the previous discussion, we said that just by varying the riskless rate, we could identify the entire efficient frontier and trace the feasible region as well. This was based on the fact that we could identify the optimum portfolio as a function of RF, that is the investment of each security proportion, that is ZK. So there would be, if there are n securities, there will be Z1, Z2 and so on up till Zn. So each of these ZKs can be identified as a function of RF, as rather linear function of RF, where C0 K and C1 K are constant, which vary only with security ZK. K. Here C0 K and C1 K are constant and they vary with the security, not with the value of RF. So all we need to identify is these two constant, and then we can vary RF to identify the entire efficient frontier. So all we need is sort of two values of RF to solve for these. Basically there are two unknowns, so all we need is two equation, two unknown kind of thing. So all we need is two values of RF to solve for these C0 K and C1 K and get ZK as a function of RF, and this will happen for each of the securities Z1, Z2 and so on. Let's look at in terms of numbers. In the previous example, we also used a value of RF to find the optimum portfolio, dominating portfolio using all these values of RA, RB, expected returns on security ABC, standard deviation, their correlations. We also had the information about RF and we could solve for these ZIs. But let's assume that RF is not there. RF, there's no restless rate. Then we can obtain these ZI, Z1, Z2, Z3 as a function of RF. Just a small contrast from the previous example where we had the value of RF, but here we are assuming RF as a function of Z1, Z2, Z3. So we get these three equations. We can rather examine them in a simple manner. So if we solve them for ZIs, we get these kind of values. The interesting thing about these values is that here ZIs are rather function of RFs. All we need to do is change the values of RF to obtain different ZIs. But in this manner, identifying the entire or computing the entire efficient frontier is rather tedious and sort of more time consuming. All we need to do is we need to just find the two values of RF. To solve for this, get any 2 points on the efficient frontier. So once we have the 2 points on this, we could identify two portfolios for two values of RF, and once these two efficient portfolios are known, we can trace the entire efficient frontier. Let's see how. Recall that we said that we can identify ZKs as a function of RF, and that would involve two coefficients C0K and C1K, which are specific to security K, and they vary with security but not with RF. So all we need to obtain the numerical values of these is two values of RF and ZKs to solve for these constants. So I only need two portfolio points on the efficient frontier for solve these two constants, and that is we only need two values of risk-free rate that are needed, because once you have the risk-free rate, we have already seen the procedure to identify two or one optimum point corresponding to each RF. So if we have two RFs, we can identify 2 points. We have seen that procedure mathematically, how to optimize and maximize the theta and then find a numerical solution for the partial differential equation and all that stuff. We have already seen that. So all we need is two RFs. Once we have RFs, we can solve for ZK from the procedure, and once we have two values of ZK and two values of RF, we can obtain these constants. So once we have these two portfolios identified on efficient frontier, we can trace the entire efficient frontier by identifying these C0K and C1Ks. And later we'll also see that we even need not go to this extent to compute these indirectly. We can directly, using these two portfolios, we can also identify directly from these two portfolios, we can identify the entire efficient frontier. To summarize this video, we discussed that the efficient frontier can be identified simply by obtaining two risk-free hypothesized risk-free rates. Once we hypothesize these two risk-free rates, we know that we can express ZKs or security proportions as a function of RF, and all we need is two risk-free rates to identify this relationship, which is defined by these two coefficients C0K and C1K. And once we compute these, we can simply trace the entire efficient frontier just by varying RF and get ZK. And later we'll see that there is an even more simple procedure to just identify two portfolios from two RFs and then mixing these two portfolios in different combinations. Because these portfolios are efficient only, the resulting portfolio set will also be efficient. In the next two videos, we'll discuss the short sales allowed with no riskless lending and borrowing problem with the help of a simple example. In this video, let us introduce the problem. Recall the statement that we made earlier that we only need two values of risk-free asset to trace any 2 points on the efficient frontier. Once we have identified these two optimum portfolios with the help of the two risk-free rates with all the optimization procedure we discussed earlier, we can trace the entire efficient frontier. So if we start by expressing RF as a function of Z1, Z2 and Z3, this we obtained in the previous discussions. Now earlier we had substituted a value of RF to solve for Z1, Z2, Z3, but now let us start by putting a value of RF equal to 2, and if we solve these equations for RF equal to, we have three equations and three unknowns, we get the values of x1, x2, x3. What are these x1, x2, x3s? Essentially, we used our optimization procedure. If you recall that equation, R1 bar minus RF equal to certain terms, wherein we could identify an equation and unknowns, in this case 3 equation 3 unknowns, and we could solve for these xi's. What are these xi's? These are optimum weights, the weights that maximize the value of theta, the slope parameter. And once we have these values of xi, it is not really a big challenge to obtain rp bar and sigma square p with whatever we have understood about portfolio theory. For example, RP bar is nothing but summation of xi into Ri bars, where xi into Ri bar, all these values are known to us. So once we have the xi values, Ri bar are known from the beginning, we can get the value of RP bar, which is this 107 upon 10. Similarly, calculating sigma p square is also not a big deal. Recall the expression w1 square sigma 1 square plus w2 square sigma 2 square and so on. In this case, w3 square sigma square, the variance terms, and then there will be cross variance term, which will 2 times w1 w2 sigma 1 sigma 2 and rho 1 2 and so on for 1 3 and 3 1, which will appear like this: variance terms, and then you'll have covariance term. So it's all easily doable. So we get the value of portfolio variance, which is this portfolio variance. In a similar vein that we computed the values of expected return and risk and identified the portfolio for RF equal to 2%, we can do the same for RF equal to 5%. So when we solve for this, we'll get two portfolios, P1 for RF equal to 2% and P2 for RF equal to 5%. So two portfolios are available. Now, what is the missing piece to identify the efficient frontier? When we said that once we have these two portfolios, P1, P2, I can identify the entire efficient frontier. But there's one missing piece. What is that missing piece information? Probably you would have guessed it right, that all you need now is the covariance between these two portfolios. Covariance or correlation, which are one and the same thing for us in this context. So once we have these portfolios P1, P2 and their covariance or correlation, then we can start mixing them in different proportions to identify the entire efficient frontier. But how to identify that covariance? A simple mathematical trick will help us here. So recall, if we mix these P1 and P2 in a 50-50% ratio, half of P1 and half of P2, the resulting combination will also be connected to the original securities A, B, C, or 1, 2, 3, the three securities that were originally part of these portfolios P1 and P2. So a 50-50 half of portfolio of P1, P2 will also be a 50-50 half of securities A, B, C. That means we are mixing them in equal proportions. So what do we mean here? So what we are saying is that, let's say portfolio P1 comprises x1 proportion of let's say xa proportion of A, xb proportion of B, and xe proportion of C. P2 comprises ya proportion of A, yb proportion of B, and yb proportion of C. So the 50-50 of mixture of P1, P2 would be nothing but xa plus ya by 2, xb plus yb by 2, and xc plus yc by 2, which will be the resulting portfolio, which we can identify using these points. And obviously we know the expected returns of securities A, B, C, and we also know their standard deviations and correlations. So we can directly identify this 50-50 portfolio. Now the only unknown when we compute this portfolio with the help of P1, P2 is sigma 1, 2, which we can identify because now we have identified the risk from the source securities ABC, which were the original constituents. The only unknown is covariance, which we can identify now. To summarize this video, we discussed a very important and interesting trick of identifying the efficient frontier with the help of two securities. These two security portfolios, the optimum dominating portfolios, were identified by considering two hypothetical risk-free rates, RF1 and RF2. Once we could hypothesize two risk-free rates, we could identify P1 and P2 with the optimization procedure we discussed in the previous discussions. However, one challenge that still faced us was the identification of covariance or correlation between these two portfolios. But we could identify a simple portfolio, one particular portfolio that was mixture of these two portfolios, which was obtained by mixing 50-50% of these P1 and P2. And we could identify that particular portfolio, 50-50 portfolio of P1 P2, because the constituents of P1 and P2, that is ABC, were also mixed in a 50-50 proportion to obtain that resulting P0 portfolio, which was 50-50 P1 P2. Once we could identify that portfolio P0, which was a combination of 50-50 P1 P2, we can put covariance between P1 and P2 as unknown and identify the value by solving for that covariance. And now that we have covariance between P2, our entire problem is solved. We can identify the entire efficient frontier. In this video, we'll conclude the numerical example that we started in the previous video and concretize our understanding of short sale allowed case with no riskless lending and borrowing. Recall that we have these information points, that is expected return of securities ABC, their standard deviations and correlation. and we could find two portfolios corresponding to risk-free rates RF1 and RF2 equal to 2% and 5%. The portfolios P1, we could identify the precise weights of security 1, 2, 3 or ABC in these securities, and P2 with securities ABC, the weights invested in this. We are using A, B, C interchangeably with 1, 2, 3. Now, recall we said that 50% we are trying to identify a portfolio, its expected return and risk with 50% of P1 and 50% of P2. Because P1 itself is made of A, B and C and P2 is also made of A, B and C, the 50-50% weight would essentially mean that 50% of this, 50% of this and 50% of this. That is, if I have X1 invested 14 by 18 weight in P1 and 7 by 20 in P2, then the weight of A in P 50-50 of P1 P2 would be 14 by 18 into 1 by 2 plus 7 by 20 into 1 by 2 weight in A. Similarly, 1 by 18, this one into 1 by 2 and X2 into this 1 by 2. Similarly, this into 1 by 2 and this into 1 by 2 in security 3 or security what we are calling as C. Now we know the proportionate amounts invested in A, B and C. We know the original formula for three securities. We can compute the portfolio with portfolio variance, where these three securities with the given proportions are involved. This is nothing but W1 square sigma 1 square plus W2 square sigma 2 square plus W3 square sigma square, and then cross product terms like 2 times W1 W2 sigma 1 sigma 2 rho 1 2 and so on. The only reason we could do here because we have identified the weights of security A, security B and security C by taking the average of these weights, summation of these, this half of this and half of this, half of this, half of this and half of this and half of this. Once we do that, we get the portfolio variance which we saw in the previous here 21.859, the portfolio variance. But we also said that this portfolio variance is a combination of P1 P2 in 50-50 ratio. So we can also formulate the portfolio variance with the formula of two security, that is x1 square sigma 1 square and so on, x2 sigma 2 square and 2 times x1 sigma 1 x2 sigma 2 and so on. Here we know x1, we know x2 50-50%, we know sigma 1 sigma 2 we have already identified. The only missing piece here is rho 1 2. So we can keep this as, like we said and discussed in the previous video, as unknown variable. So only sigma 1 2 is unknown while sigma p square is known. All these terms are constants, so we can obtain sigma 1 2 here, which turns out to be 19.95. So now we know the variance and covariance of two portfolios on the efficient frontier, and now we can keep on mixing them in different proportions to identify the entire efficient frontier. To summarize, in this video we concluded our numerical example and we saw how using the basic properties of original ABC portfolios, which were the main constituents of portfolio P1 and P2, we can identify a portfolio P0, which is a sort of 50-50 combination of P1 and P2. With the property that P1 and P2 are essentially coming from A, B and C, we can also identify the variance of P0 and therefore resulting covariance of between P1 and P2. Once we have the variance of portfolio 1 and 2 and their covariance, we can now identify any combination of P1 P2 and then essentially we can identify the entire efficient frontier that joins two efficient portfolios that are P1 P2. In this video we'll discuss the riskless lending and borrowing case with short sales not allowed. We'll discuss only how to formulate the problem equations, but the actual derivation of mathematical formulations is outside the syllabus and mandate of this discussion. Recall, we said that with riskless lending and borrowing, the one tangency portfolio was optimal, and this portfolio could be identified by maximizing the slope. Remember the theta slope of the line connecting the riskless asset RF and the efficient frontier, if you recall this maximization procedure. The objective function that we decided to maximize the slope was the portfolio that lied on the efficient frontier theta slope rp bar minus rf upon sigma p. This is what we maximized. Now we had a constraint, that is summation of xi equal to 1, that was well constrained, but now because short selling is not allowed, then we need to put an additional constraint that xi is greater than 0 for all the i's. That means no weights can be, or we can put an equality also, but the point is that no weight should be less than 0. So now this objective function is non-linear because it involves variance terms. This becomes a quadratic programming problem, and now this can be solved using computer programs. To summarize, we saw how to formulate equations for riskless lending and borrowing with short sales not allowed problem. We saw that essentially it's a quadratic programming problem with one additional constraint, that is summation of weights being greater than 0, and therefore we would require computer programs to solve this. In this video, we'll formulate the equations for riskless lending and borrowing not allowed and short sales also not allowed. Again, the actual mathematical derivation is outside the syllabus and mandate of this discussion. Recall that we obtained the efficient frontier by minimizing the risk levels for the given level of return. So we said that for a given level of risk, we'll maximize the return, or given level of return, we'll minimize the risk. So for example, once you specify the level of expected return from the portfolio, then you minimize the risk and you get 1 point on the efficient frontier. So essentially what we are saying, that you choose a level of expected return, and for that return, whatever point gives you minimum risk, that you take that point. And also that you trace this efficient frontier between two particular points. One is minimum variance point and this is maximum return point. Between these 2 points, you trace the entire efficient frontier. So first you fix the return, which is your portfolio return RP bar, which is nothing but obtained by this equation. So you fix the return, all the return points, and for each return point you minimize the objective function. What is objective function? Sigma square p, which is the risk or variance of the portfolio. We know the expression for n security investment in a portfolio, which is like this: summation xi square sigma I square plus summation I equal to 1 and j equal to 1 to n xi xj sigma ij, where I is not equal to j. Again, this is subject to the wealth constraint, that summation of all the weights should be 1, which is the wealth constraint, that we are investing 100% of our wealth. And another critical constraint, which is xi greater than or equal to 0, that is xi cannot be less than 0 or short selling is not allowed. In that case, this formulation again becomes quadratic. So you can vary your RP bar from minimum variance to maximum return portfolio and trace out the entire efficient set, which is again a quadratic problem. To summarize, in this video we discussed the case where neither short selling nor riskless lending and borrowing was allowed, and we noted that we could identify and trace the entire efficient frontier by minimizing the risk for each level of given return. Again, with the short sale not allowed case, this again becomes a quadratic problem which requires computer programs to solve the entire efficient frontier. In this lesson, we have already discussed how to find the optimum portfolio, the tangent portfolio, in the presence of a given riskless rate. So if we have the riskless rate or risk-free rate, we can identify this optimum tangent portfolio. Let us apply this in this video and find a more rigorous proof of CAPM. Let us recap our previous analysis of finding the optimum point on efficient frontier. We noted that there was a slope function theta in the presence of risk-free rate, which was written as RP bar minus RF upon sigma p, that we maximized through partial differential equations, where derivative of theta was taken for all the securities, that is xi's. For this set of equation, d theta upon dxi, it was set to equal to 0 to find the maximum slope value. And we got, if you recall, we got the following set of simultaneous equations. There were n set of equations corresponding to each of the security I and n unknowns, that is xi's, that we solved for. Now please recall a very important assumption in CAPM, that all the securities held in the market portfolio are exactly in the same proportion as in the actual market. Let us see how it makes all the difference. In the actual market, you would have market portfolio RM as the weighted average of all the individual securities. So we can write the actual and expected returns as weighted averages of individual security returns, where xi's are the ratios of market capitalization of that security to the aggregate market capitalization in the actual market. So in the actual market, I can also express this covariance relationship as expected value of RK minus RK bar into RM minus RM bar. This is the expectation version of the covariance relationship. But we already know that this RM is sort of weighted average of individual returns for both actual and expected returns. That is RM equal to RIXI dash for actual version and RM bar equal to the summation RI bar into XI bar. So in the expected version, let's make use of these equations. So we have, again, this is our covariance expression, where we can multiply each of these values with RK minus RK bar and expand the expression. It will appear like this: x1 dash into rk minus rk bar into rn minus rn bar, and then x2 dash and so on, and up till xn dash. We can further simplify because x1 dash is the constant term, x2 dash is constant, and so on up till xn dash they are constant terms, so we can take out, and inside this we only have the covariance expressions. Let's simplify further. So what we have is the complete covariance expression in the form of x1 dash into covariance of 1 and k, x2 dash into 2 and covariance of 2 and k, sigma 2k, k dash into covariance, here it's more of a variance of k square. So one term will be variance, all the other are covariances. So we can further write it like this. All of them being covariances, only one term is a variance term. Now let us compare with our optimum portfolio that we were discussing earlier. We have already obtained this expression for the optimum portfolio where x1, x2, xk's are the optimum weights in the tangency portfolio. Lambda is our constant, and this was equal to rk bar minus rf bar. Please clearly note the distinction that these xi dash, x1 dash, x2 dash are the investment in actual market caps terms, while this xn, x1, x2 these are in that tangency portfolio, the optimum portfolio. But with the CAPM assumption, these x1 dash are same as x1. The CAPM assumption is that in the tangency portfolio, the market cap or the ratio of individual security investments in the tangency portfolio is same as the actual market. That means x1 dash is equal to x1, x2 dash equal to x2, and so on. And with that argument, this covariance term becomes equal to this rk bar minus rf bar. So what I'm essentially saying that I can take out this lambda here and equalize these two parts, comparing RHS and LHS. What essentially we get is that rk bar minus rf equal to lambda times covariance of rk-rm, which is based on the assumption that xk dash are the actual market proportions, that is xk equal to xk dash. Now here, how do I identify the value of this lambda constant? It's pretty simple. Recall it was rp upon sigma, something like rp minus rf upon sigma square p. But even if you do not recall, all I need to do is consider rk as same as rm. Let's say, what about market portfolio? So in that case, if rk is equal to rm, then rm bar minus rf equal to lambda times covariance of rm with itself, which is nothing but variance of rm. And with that argument, what we essentially achieve is that covariance of rm is sigma square m, and therefore this is sigma square m. So lambda value is obtained as this, rm bar minus rf upon sigma square m. So we get a value of lambda using the fact that this market portfolio will also, this will hold for market portfolio as well. So now that we have got the relationship for lambda, let's substitute that in our original model, this one. So we get rk, this one actually, rk bar minus rf equal to this lambda term into covariance of rk into rm. We'll make a slight simplification. We'll say that for each security, its a coefficient beta k, which is sort of sensitivity of the security to the market, is nothing but covariance of rk with rm upon sigma square m. That is, this divided by this is the beta of security, what we call as the sensitivity of security. And the resulting equation becomes nothing but CAPM, that is rk bar equal to rf plus beta km times rm bar minus rf. This is the most celebrated CAPM model or security market line equation for this particular version of standard CAPM, where beta k is the sensitivity of the security k with market, which is interpreted like this. If there is a 1% movement up or down in market, security moves up or down by beta percentages. To conclude and summarize this video, here we learned in a more rigorous manner how to prove CAPM. We used and utilized our newly developed understanding of tracing the efficient frontier by optimizing the slope parameter theta. We maximizing the slope parameter theta, which was rp bar minus rf upon sigma p. With this maximization procedure and an assumption that the tangency or optimum portfolio has the same and identical proportionate investments into different securities 1, 2, 3 and so on, which is in the actual market, so that this tangency portfolio is sort of replica of actual market. With this assumption, we could obtain a version of standard CAPM like this, which is the equation of security market line also. To summarize, we discussed that in the presence of infinite risk-free lending and borrowing, there is one portfolio that is best among all. In order to identify this portfolio, we maximize the slope term theta, where numerator is excess return and denominator is portfolio risk or standard deviation. With a few simple adjustments, this optimization problem can be converted into linear programming with n equation and n unknowns. The solution to this problem effectively results in HIs, that are portfolio weights, and in turn the identification of key portfolio parameters, that is the optimum or market portfolio expected returns and risk. Next, we examine the case with short sales allowed and no riskless lending and borrowing. In this case, we noted that the entire efficient frontier can be identified by changing the riskless rate. We also noted that since the combination of efficient portfolios are efficient portfolios only, so all we need to do is consider to hypothesize risk-free rates and identify two efficient portfolios. Now, mixing these two efficient portfolios, we can trace the entire efficient frontier. However, this exercise requires identifying covariance or correlation of these portfolios. It may be noted that an interesting portfolio, which is a 50-50 combination of these two portfolios, can be employed in an ingenious manner to identify the correlation between the two efficient portfolios. Through a simple numerical example, we demonstrated the entire procedure. Lastly, we discussed, in the absence of short selling, the efficient frontier with and without risk-free lending and borrowing. We noted that the problem has become a quadratic problem and the complete derivation is out of scope of the discussion. Next, we discussed the rigorous derivation of CAPM by maximizing the slope parameter on the efficient frontier. Finally, we close the discussion with the summary and concluding remarks.